And I want to welcome all of you here to this activity, which looks like it's going to be a lot of fun over the weekend. The SETI Institute, just in case you're wondering, this is not Area 51. There are no bodies stored in the back in the refrigerator, so you can get that out of your mind as you wander around here. One of the things that I think is you're going to see as we go through this weekend and through the early presentations after I'm done is a group of really good scientists who have got some great and exciting data that will be used as input to the gaming activity. And I think you'll find there's not only good science, but a great diversity of science. We have people here at the Institute who do a range of things in astrobiology, people who look at asteroids that you'll hear a little bit about later on, planetary protection, which is part of the whole story as we send our craft around the solar system. You're going to hear about people who've spent a lot of time discovering other planetary systems, a wide variety of things that will be serve as input to what you're doing. We have somebody who's very interested in those crazy moons of Mars, Phobos and Deimos. That's the one with the dog, not Phobos or Deimos, but the guy who's interested in those things. So I welcome you. I think it's going to be a lot of fun. People will be wandering in and out throughout the weekend to see how it's going, other scientists from the Institute. Glad you're here. I hope you have a great time. And again, welcome to the SETI Institute. So let me turn it over to who's next on the docket. Josh.
Yeah, so I'll just give you a little bit of logistical information for all the guys that are new to the SETI Institute here. Because I know a lot of the game developers probably haven't been here before. So this is going to be our home for the weekend. This is the SETI-Jam Central. And in the back, you guys saw there's food. There's also food available in the fridges there. So anytime you feel hungry or want something to drink, feel free to go back there. If it's labeled, don't eat it. If it's not labeled, should be good to go. Restrooms are also in the back. Just go behind the kitchen a little bit. Also, if anybody needs just a quick crash pad, take a nap after you're tired of coding for the next 20 hours, there is a little crash pad back, across from the kitchen as well, just pretty much right behind me here through those doors. So, and if you have any questions, throughout the weekend, you can come to me. Lee's going to be around, who's been doing the website. If you have any questions just about web things like that, like David said, we've got some really great scientists coming up. So. Before we get into the actual science talks, one of our advisors is going to give a little bit of a run through of the actual rules of this game jam. So every game jam kind of has a few themes and rules set up. So I'd like to turn it over to Ryan Williams, who is going to give us a quick run through of the whole layout for the SETI-Jam.
Thanks, dude. All right. So why is it that game jams have rules? Why is there a theme, a limit? The reason is because creativity comes from limitations. Creativity comes from being constrained. Something about the human mind means that when somebody's like, yeah, you can't do this stuff, your mind is just like, oh, I want to do that. It gets real excited. So that's what I think. That's why a lot of game jams have these limitations. If you're just given something complete freedom to do whatever you wanted to, you'd come up with some bogus stuff that sucks. So we give you a limitation. So we're going to give you a two-part limitation for this game jam. The first part is, I want to show this. Lee, this is why you're here. Yeah. What was the thing? Oh, that thing. Nice. You want to show the data page, right? Yeah, data page. Give me the data page. So the first part is that you should make your game based on the Drake equation. Now, the Drake equation is an equation that has multiple terms, and each of those terms represents something about the probability that we will encounter intelligent life in our lifetimes or ever. Actually, it's the other page. Let me just go to the this page. This beautiful graphic shows us the terms of the Drake equation. So there's 7 of them. So you should make a game based around one of these terms. So there's a lot of interesting stuff here. So there's the rate of star formation one, which could lead to some interesting ideas about planetary physics, gravity, rules of elementary particles. And then there's the one at the other end, the length of time that a civilization exists. What ends a civilization's lifetime? Why does it stop? How can you prevent it? Interesting questions to ask when you're making a game. So that's part 1 of our theme. Make sure you pick a term from the Drake equation. The second part is data sources. Use a data source from a SETI scientist, from a SETI venture. We've put together this page right here as sort of like a overview of the data sources that are available. But I'd like to emphasize before I wade into it a little bit that this is not an exhaustive list. This is just stuff that's available on the web. So if you find stuff that on your own or something that you're talking to somebody in person that you can use as a source of data, go for it. And if there's something I missed and I should just put it on this page, just come talk to me and I'll put it up there. Or talk to Lee. Lee can do a lot more stuff than I can. So yeah, so there's some data sources that are immediately pluggable into games as sort of assets. So these asteroid mining resources links have links to 3D models of asteroids. Super cool. There's images. There's images from Cassini of Saturn and its moons. There is data that's a little bit raw. So there's this exoplanet archive which contains semi-raw data from Kepler. And that data, it's going to be difficult to process. But if you can do something interesting to that, that would be really cool. Oh, and Horizons, this is really cool. This is a data source. This contains orbital information about all the planets and small bodies within the solar system that we know about. So there's like a coordinate system, and there's like velocities, and you can get a time sequence for the future. It's pretty cool. There's also 3 models of the Kepler spacecraft, and Kepler planets found, lists all the planets. And I'm not going to go through all these data sources. You should just go look at this page. It's linked from the SETI-Jam website, and browse through it, get an idea for what you might want to use. So what we're going to do now is, one of the things you'll notice about this page is that it has links to scientists. And these are the people who you want to contact when you, these are the people responsible for this data. So these people are going to speak and introduce themselves and say what is exciting about their data, what is exciting about their field of research, and hopefully that gets you excited about using their data. So we're gonna start doing that now.
Awesome. Thanks, Ryan. So yeah, we're going to go right into our scientist round now. We've got some really amazing, world-class scientists that are going to be talking with us about, well, how do we actually take advantage of all of this research and data? These guys have been doing this, for a career, and have done some really amazing research on everything, like Ryan's saying, from asteroids to exoplanets, all across the board. So our first scientist up does some amazing work with Mars exploration. He actually goes and explores Mars here on Earth. And I'll let him tell you a lot more about that, because it's really amazing and just blows my mind every time that I've heard him talk about it. So our first scientist is Pascal Lee.
Hi, so I'm Pascal Lee. David Black was mentioning somebody who was interested in the moons of Mars. I count myself among them. I'm not sure he was referring to me or not, but I hope that you will be interested in them too. So I'm a planetary scientist here. And I'm very happy to be with the SETI Institute because of the breadth of research that is hosted at this organization. So I don't know if I have control of the slides. Okay, thanks. So this is Lee, our webmaster. Yep, the equation. So I did want to, this wouldn't be a SETI Institute talk without at least a quick run-through of the equation and its terms so that you, those of you who are not familiar with it, at least will get a sense of it. So it's a formula that gives you, in principle, if you knew the value that these 7 terms take, R, F, N, F, 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 and L, it's a formula that would give you the average number of civilizations that are in our galaxy at this time. Okay, so it's equal to the rate of star formation in our galaxy times the fraction of those stars that have a planetary system around them times the number of environments within each planetary system that is suitable for life, and we translate that into has liquid water available for a substantial length of time, times the fraction of those environments on which life actually emerges, times the fraction of those planets on which there is life where it eventually becomes intelligent. And by that we mean something that is a life form that is capable of changing its environment through technology, and that begins with warming a cave with fire. Okay. So that's the human being maybe 1 million years ago, times a fraction of those societies that are intelligent that become a communicating civilization, F sub c. So all the F terms are a number between 0 and 1. And then the final term, L, is the longevity, the average longevity of a civilization in our galaxies. Some of these terms, so the F terms are a number between 0 and 1. Some of these terms are known relatively well. So the rate of star formation, for example, in our galaxies, anywhere from 20 to about 50 stars a year. Other terms are completely unknown. And in fact, we only have the Earth as an example. And even in the case of the Earth, we don't know what the longevity of our civilization is. But if you knew the exact value of these numbers, you would come up with a ballpark estimate of the number of civilizations we have right now in our galaxy. And interestingly, depending on whether you are optimistic, pessimistic, or if you consider yourself realistic, you can find a number n that is much smaller than 1, in which case we are really an exception, not only at the scale of our galaxy, but in the universe. Or you can find a number of n for n that's relatively large, possibly 10,000. And so it's really interesting that, and so what many of us are trying to do at the SETI Institute in the research that we conduct is to address one or several terms of the Drake equation. And that gets my dog very excited. Okay, so I think I'll just leave it to that. There are many people here that can answer your questions about this equation if you'd like to have more information, but to me, it's a very powerful tool. Yep.
One point of clarification. If you look at L, an important part of this is something you may want to factor into your game, and that is that it's actually the length of time on average that a society communicates. So you can imagine any number of ways in which communication may end. The society may blow itself up. They may decide to go radio quiet. There's any number of these things. So as an element of your gaming, you might want to think of it that way as a part of it.
Yep, thank you. And incidentally, if any one of these terms is close to 0, that will bring the number n down for obvious reasons. Okay, so that's a very important thing to realize. So I'll just go on with my talk. I'll talk to you about exploring Mars. Here at the SETI Institute, we are not just interested in incidentally, the scientific exploration of Mars, but also in the human exploration of Mars, and I'll talk to you about that in a second. So here you have our local neighborhood to scale, not in terms of distances, of course, but in terms of size. So that's the Earth. Our moon to scale, where gravity is 1/6 of what it is on Earth. Then we have near-Earth asteroids that are roaming around. And then in orbit around Mars, we are aware of 2 little moons called Phobos and Deimos. We don't know what they are. They might be captured asteroids. They might be leftovers from Mars' own formation. They could be bits and pieces that were blasted off of Mars and reassembled into little asteroid-like bodies around Mars as well. So these are the 3 main hypotheses for them. And then there's Mars itself, where gravity is 38% of what it is on the Earth. Okay. Now, by human standards, Mars is really a godforsaken place. It's really hostile, and in spite of the landscape that looks, welcoming like Arizona or Utah, you have to realize that it's a very harsh environment. And you would die as quickly on Mars as you would on the Moon if, for example, you sprang a leak in your spacesuit. But having said that, in my view, it's a very exciting planet to go explore, not just with robots, but also with humans, physically explore this environment, because there's a real chance that Mars might have harbored life in the past and might even harbor life today. Okay? And, of course, the way our search for life on Mars is guided is to follow the water. That's the name of the strategy that NASA adopts, because on Earth, everywhere where there is clean liquid water, there is life in it. And everywhere where there is life, every form of life on Earth needs liquid water at some point. Okay? So there's a bijective relationship between life on Earth and liquid water, which is why we're using liquid water as a guide to search for life on Mars. So we go to places where there were once water on Mars in liquid form, or we go to places where we think we might find water today. Okay? And so on Mars today, you might find an abundance of liquid water in the deep underground. When you go deeper, the temperatures rise. Meanwhile, there's plenty of ice on Mars. At some point, this ice that's in the ground turns into liquid water. There has to be liquid aquifers inside Mars. That, in my view, is the holy grail of where we need to search for life, for living life today on Mars. So here's where my research takes me with our teammates. We go every summer to this incredible place in the Canadian Arctic. It's called Devon Island. It's the largest uninhabited island on Earth. We essentially have the island to ourselves every summer. There's a large impact crater there called Houghton Crater. And the landscape on this island is really incredibly Mars-like. And I'm showing you on the right here two columns of images. The far right column is showing you pictures of Devon Island, and then the left column, the column to its left, are essentially images of the surface of Mars at the same scale. And we're seeing that there are a number of geologic features that essentially have equivalence, at least morphologically, in terms of their looks, between the Earth here at this location and Mars. So we're very intrigued by these similarities. So we go to this place every summer to try to understand the geology, to try to understand where life hides in such a setting. And that way it gives us some background experience for how to interpret the Martian landscape or not. Okay. As we go about our science, we are also interested in using this place to learn how to explore. And so we bring along spacesuits that are developed by industry. We have Humvees that actually have a tall cab in the back that serve as simulators for pressurized rovers in the future. And we go about our field geology and our field biology sometimes in a simulated Mars exploration mode. Okay, so we constrain our outings, for example, to doing them using a spacesuit, and also limiting the time we have to do our field work by the time that one would reasonably have with a spacesuit on us. So that could be 4 to 6 hours or so. We also run a camp that is, in some sense, a precursor for what a Mars base might look like, at least functionally, in the future. And that, I think, is what we need to set up sort of as a specific goal for humans on Mars, is set up a base, an infrastructure, a bit like a research station in Antarctica, and then use that as a springboard to go explore the rest of the planet. What we then do is we go back to Mars, and there are vast data sets of Mars images. You can find them at, for example, the Planetary Data System, PDS, the NASA PDS repository. You can click on the planet of interest. You can find images of their surface. You can find maps as well. And in this case, I'm just using Google Mars, which is also a very nice resource. And you can plan a road trip on Mars. You can pick a site where you might want to have your Mars base. And then you plan a road trip from that Mars base to go explore sites of interest, volcanoes, for example, or canyons. And then things might happen to you along the way. You might have to stay put because of a dust storm. for a few days, or you might have to go around a canyon that wasn't quite visible in the imaging, etc. So, or at least a drop. And so what we try to do here is we plan a traverse at a certain scale on Mars, and then we try to replicate that on Devon Island. We have our Houghton crater, our impact crater, as a central feature, and then we essentially try to see what it would take to explore a similar feature on Mars by learning how to do that in the Arctic. And so I think what we would love to see as a game, I mean, that's sort of coming up in my head right now, is some sort of a tool that would allow you to, first of all, select the place where you would set up shop on Mars, a base. Where would you do that? It would have to be a safe landing site for people to get there safely. It has to be visible from the Earth a lot. Okay, so you don't want to be, for example, in the bottom of a narrow canyon, because then you can't see the Earth very often. But you also want it to be, so you want it to be safe enough and open enough for landing, but then you also want it to give you access to sites of interest. Okay, and of course they have to be within 100 kilometers ideally, if you can. So there's an optimization process here that needs to take place for you to select your landing site, and then from there on you have to plot traverses, and you have to make sure that if you break down, you are able to either walk back or wait for another vehicle to come pick you up. Then you have the clock ticking in this process, and then you also want to set up caches of supplies, okay, to be able to survive. That, in my view, is just a quick overview of the types of challenges that a game could offer, sort of the planning of a mission to Mars and how you would explore the surface of Mars with specific realistic constraints. As well, we're planning in the short term a visit to the 2 moons of Mars. And in fact, I'm working right now on a discovery mission. It's a robotic mission that will go explore the 2 moons of Mars to determine their origin. These 2 moons are very exciting scientifically because we really don't know what they are, and so depending on what they turn out to be, that's going to have a number of consequences for our understanding of the solar system. But as well, they are likely to play a very important role in the human exploration of Mars. We are thinking that they might be used as stepping stones to allow humans to get to Mars orbit first, have a platform in space from which they can observe Mars, but also have an infrastructure in Mars orbit. And they might even be able to derive resources from these moons if they turn out to have water. Okay, and so that's a big mystery right now. We don't know what their water content is. That, incidentally, is one of the things that our little mission will help determine. But they might have resources for humans to explore Mars more readily. If they turn out to have water that's extractable, then all of a sudden you could break down the water and turn it into hydrogen, oxygen, and have rocket fuel for your return trip. And so there are a lot of things that are hinging from the standpoint of Mars mission architectures on whether or not these moons have water. As well, these moons might be used to cache samples. Okay, and so the idea here is that we might collect over the next decade rock samples from different places on Mars, gather them on one of these 2 moons, and then have humans go collect these samples, analyze them once they've been quarantined on these moons for a while, and then you can explore this place. So I think I'm running out of time, but this is just an intro for you guys.
All right, so we're going to roll right on through. We've got a number of other scientists up here to talk with us about all the exciting research. So our next speaker to introduce what's going on with the Allen Telescope Array and some of the exciting work of the actual search that SETI is doing. So please welcome John Richards up.
So I have a presentation here, and I don't know. That's pretty. Okay. Okay, so my name's John Richards, and I work at the Allen Telescope Array, and What we do at the Allen Telescope Array is the part of SETI where we're receiving radio signals from outer space and analyzing the signals to see if we see anything intelligent in the signals. So raise of hands. How many of you know of the Allen Telescope Array? Most of you, some don't. So I'm going to go through very briefly what it is. So it's the Allen Telescope Array, and I'm going to refer to it as the ATA. So I got a map here of where it is. So this is where we're at right now, basically. And if you drive 6 hours north, you go to Highway 5 up to Reading and then east, that's where the Allen Telescope Array is. So it's in a very remote area where there's not much stray radio signals. There's no houses nearby. I mean, a couple miles away there are, but you know, there's no big radio stations. Reading is over the mountains. Reno's over the mountains. So it's pretty much radio quiet there. And I just noticed last week that on Google Maps they got a really good new photo of the ATA, and it shows our whole facility. So those the white dots there are the dishes. We have 42 of them, and they're each 20 feet in diameter. So this is what we use, and the green building right here is where all our computer equipment is, and that's where we do the data analysis. So every night, basically from 7 at night till 7 in the morning, we're looking for radio signals. So what do we see? Well, let me give you an example of something we see when we're looking on purpose at something. You'll see here charts of Voyager 1. So Voyager 1 is out way past Pluto. We can just barely see it. So if you look at, if you can see our data that we have, it looks like static, right? Like it used to look like on a television. But you can see there on the right, there's that really faint white line. So that is the signal coming from Voyager 1. We're receiving it very faintly, and it's tilted because of the Doppler effect, because we're rotating and it's going away. So the frequency is actually shifting in time. Rosetta's just made the news this week. Where has it landed yet? Landed its probe on the comet? Next month? Okay. Yeah. So we're able to see Rosetta. That's a very strong signal. Another one is the Cassini spacecraft and New Horizons and the ISEE-3 spacecraft. We can see their data, but we also see things in outer space. We don't know what the signal is. So I have on my website 500,000 of this waterfall data. Now most of the data looks like nothing because it's static, just total static. But occasionally you see a really goofy signal. Occasionally we see signals that we don't know what they are, and we go back, we look in 5 minutes, 10 minutes, an hour later, and it's just not there anymore. So there's a lot of very strange things. Some of the signals, if you look through all this, it's very exhausting looking through these every day, you know, several 100,000 of them a day. Some of them look like a slinky. I mean, actually, I think that's something, some satellite is around Earth is doing that. But one of the things that we've been looking at constantly is the Kepler field. The Kepler mission has been looking at a 10 by 10 degree section in the sky, and we have a catalog of 103 top candidates where they think these planets might have life. At least they're worth looking at. So we've been kind of concentrating on those. So we have gobs and gobs of this data for you guys to download. And if you look on the data site that is listed on the SETI-Jam page, under my page, you'll see the link to all this. And you can actually you can get into a browser and then browse through all of them if you want to, or you can download them automatically. But don't be downloading all of them because it's close to 40 gigabyte. And so do a very small section. And also in the green window here, I show that I provide you detailed data on every signal we've seen in all those 500,000 waterfall plots. So a lot of the waterfall plots, maybe 90%, look like total static to us, but our system picked it out that maybe there was a pulse or something in there. But Another 10% though has something interesting, and can you actually create some game or something that's using these signals, this signal data? That's part of the challenge. Oh yeah, okay. So if you do look in depth at our signal reports, you'll see there's 5 steps, and there's we call target 1 on, target 2 on, target 3 on, all the way up to 5. So what commonly happens is we will see a signal and we'll say, hey, this looks interesting, let's investigate this. I don't say this, but the computer system is trained to say this to itself. It got to go look. So what it does, it looks off. It actually looks away and does the same observation, the same frequency. And if it sees that signal, when it's looking out in the other direction, it knows that was radio frequency interference. All right? But if it doesn't see the signal, well, it says, hey, well, it's worth going back and looking again. So it does a series of 5 times. It looks on, off, on, off, on, off, and if it ever gets up to 5 cycles, we get an email saying, hey, this is something you should look at. And this only happened several times. And one time it was because I had a setting wrong in the system. And sometimes, you'll lock on to where you're looking at a spacecraft or a satellite that's moving slowly is in your field and you don't really know it, and that kind of thing. So every time it's always been explainable, unfortunately. So all this data is downloadable, and I tried to make it all in the images are in PNG format, and the signal reports are all in JSON format, which I thought was the easiest way to disseminate the data. So here's what most of the data looks like. It's just static. So our job is to look at the static and try to find something in that, something that's strong enough that pops itself out from the static. So if you look on the data page, you'll see in my listing I have links to all this stuff. We have 500,000 of these signals images. We have the observing schedule. So every night I post the in JSON format the schedule for the next several nights, so when we're going to be looking. So you know when to get on. When during the day we're not looking, it tells you all that. And also I give you information to look up all the signal reports. And if you really get hardcore, I can give you some binary data. The problem with the binary data is it's too huge. It's the smallest one I have is 2.5 gig, usually like 40 gig, just for like 100 seconds of data, 40 gigs. So it's kind of hard for our servers to download that all the time. But one challenge I do have, I've had this for several years. I asked the guy that manufactures the dishes, give me your CAD drawing, because I'd like to someday create a game or something, and give me a CAD drawing of these dishes. And he did. But it gave me it in IGS format. It's the standard format of these mechanical drawing, and it's got like 100,000 triangles, and it's not usable in a game. So what you got to, if somebody knew how to do this, get this into a program, which I don't have the right program to do this, and I'd love to know what program you do this in. Get this in and clean it up. Change all these polygons that are at a cylinder, actually make it into a cylinder instead of all these thousands of polygons that define the cylinder, that kind of thing. And get it down to a decent number of polygons where we could actually use this kind of universally in games. And I'd like to use it on my website, maybe do a WebGL program. That would be kind of fun to do. So that's a big challenge. You'll be on my favorite list if you can do that for me. Yeah. So visit my website often, SETIquest.info. On the menu on the left side, you'll see I've got some extra information, and I show the status of our observing, and you can see what we're observing every night and our schedule. And all this data that's on my website is actually downloadable via JSON files, and you can use that freely. So good luck. If you got any questions, just ask me. I'll be here all weekend.
Thanks, John. So for the next round of presentations, we're going to go a little closer to home. We've got a couple scientists here, maybe more than even just you guys, that are looking at asteroids, near-Earth asteroids, the shape of asteroids, density of asteroids, everything about them, and they do some really, really neat work. And I think there's a lot of good information that could be put into the games, with what Frank and Michael have. So we're going to introduce. Are you guys coming up together or both? All right. So Frank Marches and Michael Bush.
So we're gonna hold the microphone like this, okay? And we're gonna speak close to each other. We have 5 minutes.
Let go, please.
All right, you start. Because you
Okay.
explain what my...
Lee, can you help me with the slides here? Also, thank you for bringing up some of our data here.
That's what you don't talk about that.
Should be right there. Okay, get the slideshow started here. So what you see there on the screen is a projection of all known objects in the inner solar system out to the orbit of Jupiter as of this morning. That's everything that we know of. That's individual objects being tracked. There's about half a million objects in there, and they're divided into different populations. Most is the main asteroid belt between the orbit of Mars and that of Jupiter. There's also a bunch of comets, and then all the red dots, which are the near-Earth asteroid population, which is what I personally work on.
So we call that asteroids.
Now, in the near-Earth population, there's about 10,000 objects that are currently known. Of that, about 1,000 are bigger than 1 kilometer in diameter, and the rest are that are known are mostly a few hundred meters across. Now, they may seem very densely packed there, but that's an awful lot of space, and the objects are pretty small. They're about as thinly spread as a pinch of dust scattered across this room. So there's two types of data I'm going to show you here. The first is the Horizons database, which you heard mentioned before. This is maintained by the Solar System Dynamics group down at the Jet Propulsion Lab in Pasadena. You have the address here. And that lets you query the database and get the position as a function of time of any one of those several 100,000 known objects. I've pulled out one example here. This is the asteroid Tutatis. It's number 4,179. You may not be able to see that in the screen grab. And I've just, in this particular case, requested give me its position relative to the center of mass of the solar system at 1 hour intervals for the next year. And you can go through and select any object, different options for position, velocity. You can say I'm standing at this point of the Earth, is it up at this time, so on. Now, the other part of observations that I do more directly involves asteroids' shapes. So I said they're very small. But we want to understand what small objects like that look like. When you get to a size range smaller than 100 or so kilometers across, things stop being round because they have enough strength that gravity doesn't collapse them down into spheres or ellipsoids. And so we end up with complicated shapes. You see here some data that I got back in 2012. Again, Tutatis, observed with radar imaging from NASA's Deep Space Network site at Goldstone in the Mojave Desert. And here you see the radar image. We also have the 3D shape model. 3D printing is fun. And we also have verification of that model would derive from the radar images in this case because the Chang'e 2 spacecraft, which was a project by the Chinese Space Agency initially orbiting the moon, was flown out of Earth from space entirely such that it flew by Tutatis and took this series of images. So the shape model we have for Tutatis is right now pretty good, except for the area right here at the large end of the asteroid, which was not seen particularly well until we actually got these pictures, and I haven't gotten around to updating it yet. But that shape model and a bunch of other ones of different asteroids are available at this website, and you can upload these files. They're .obj is in units of kilometers. It just gives you the triangular mesh that specifies the surface, and you can put that into whatever program you want. I know a lot of people like the Kerbal Space Program. Kerbal cannot actually handle something like this because it treats everything as points and spheres. Totatus is not round. Try to plot orbits around that thing. Be a little exciting. And I hand off to Frank.
Okay, so I'm gonna give you a kind of. I didn't prepare anything. I don't have any slides because I think it's. Yeah, I knew you will show stuff already. I'm not gonna show the exoplanet stuff. I'm gonna talk about the asteroids. So one of the reasons for which we study asteroids, not only because they're not spherical and we love complications, is because we want to understand how formed the planet in our solar system. Okay, asteroids are basically the remnant of the formation of our solar system. So when you study them, you kind of have an idea of the past of our solar system, but also what formed the material that where come from the material that formed the planet in our solar system. So I came to asteroids not only because I like irregularly shaped piece of rock, but also because I use what we call adaptive optics, which are this new type of instrument that allow you to get observation like if the telescope were in space. And using this adaptive optic system, now when we observe an asteroid, we don't only see a dot, we see a dot and a tiny dot nearby it, which is in fact a moon. 10 to 15% of the asteroids in the near-Earth population, so close to us, have companions, moons. So this is one of them. It's, let me see, I always forget. Thank you. Exactly. So 1999 KW4 has been discovered in 1999, the primary called Alpha. And when they observe it with radar observation, they discover that it has also a moon, a tiny moon that you have here. So if I could, well, basically the moon orbit around the primary, describing an almost circular orbit. So this is interesting because we did not expect to have moons around asteroid before 1995 when you discovered the first one. But it's also interesting scientifically. From this study, from the study of the orbit of the moon around the asteroid, we get information about the formation, about the density, so the type of material you have inside the asteroid itself. So over the past 10 years, I basically study multiple asteroid systems, and I discover various moons around main belt asteroid. The largest one, such as Sylvia, have 2 moons in orbit around it that we name Romulus and Remus. So this is interesting to study, as I say, non-irregularly shaped bodies, but why do we care that much about asteroids? Well, we care also about asteroids because they're also resources for future generations. And if you want to do a game, I think you don't want to do a game about observation of an asteroid itself. You want to do a game with a topic. And I think a good topic could be for a game to understand how you can mine an asteroid like this, how you can extract material of an asteroid like this, knowing that, for instance, it has moon in orbit around it. This is a complicated problem. Very complicated, so complicated that even NASA still don't know how to solve this issue. So we're hoping that people like you with a lot of creativity will find a way to simulate the mining of an asteroid with moons. And that I encourage you to think about that and look at our database where we put, you have your database on the website, I have my own database on the website as well. And contact us on Skype if you have any questions. Thank you.
So is Margaret here? Right. So we have on the schedule listed that Lawrence Doyle will be next. Lawrence is actually not able to join us tonight in person, so we're going to try to do a fancy, fangled kind of technology snafu later that we'll figure out after we go through with Margaret and our last presenters. So with this, I'm going to go ahead and just turn it over to Margaret.
Hi, I'm Margaret Race, and I am a biologist, so these guys do things that I don't know about. And I'm always amazed at the kind of things they come up with, and I'm somebody who kind of thinks about the real world, here and now. We're here on Earth, and we got this incredible wealth of information about basic science, and I'm thinking a little bit more about the implementation and the policy and things like that. So first of all, what I'm going to say is that I'm looking at science policy in the real world. And the 3 areas that I'll talk to you about are planetary protection. That's really what I do. Invasive species. Discovery of extraterrestrial life. What if we find it? So these things are more like the context that you might use for your games. And something called planetary defense, also linked with asteroids. So, let's see. This doesn't want to do it. Okay, so planetary protection actually, so I'm an astrobiologist. I think about life any place we can find it. And so that far left corner picture is the kind of a, where did all the stuff come from out there in the universe? And when did it come together and make a replicating system? That's origin of life to a biologist or a scientist. It's not the same as creationism. It's, okay, what happened that we got something evolving and replicating? And then the SETI people are thinking, how did it get up to be intelligent? I'll take any kind of life. It can be stupid. I don't mind. It's a microbe is still life, and I don't know how Ebola, for instance, does what it does. It's pretty simple, but I'll tell you, it does very complex things. So life of any sort is what's interesting. And when we started doing space exploration back in the late 50s. The United Nations, US and Russia and other countries got together, and the United Nations passed the Outer Space Treaty in 1967. There's over 100 nations that have ratified it, and it has a whole bunch of things about how you take care of things in space. What do you do about liability if you crash? What do you do about mutual aid for astronauts? What about assigning frequencies or thinking about space debris and all of those things? Well, it turns out that that works great when you're talking about Earth orbit, but you've never really left home. And the only ones that have really worked on some of the things on the moon and beyond have been scientists. And we don't have any rules, right? So what does it mean to avoid harmful contamination of other places? And, oh, by the way, if you bring something back, how do you make sure you don't mess up this planet? Think invasive species, and that's what I work on. So it could be microbial, or it could be something like Asiatic clams out in San Francisco Bay, or the mud snails that I worked on that came in on oyster shells after the gold rush, when they used to bring oysters from the East Coast by transcontinental railroad. So we move things around all the time, and that notion of invasive species is very, very real. Again, think Ebola. So it could be a large-scale species, or it could be something microbial. And so when we think about planetary protection, we say whenever you design a mission, you have to think about where's the mission going, what are you launching on it? Could we be sending life out there to infect Mars? If we're going out there to look for life, you don't want to be bringing it with you and then say, oh, I found it, only to find out it came from Cape Kennedy. So we think about what's called forward contamination, and we also think about back contamination. So the Committee on Space Research is a group of scientists, and they work with NASA and with space agencies all over the world. What we do is think about robotic missions and human missions, and we think short-term and long-term. So the first left column, whenever we send a rover or something, there's a lot of cleaning that's done before it goes. Think surgical cleaning room, surgical scrubs before you go into a surgery. And so those things that go out are very, very clean and don't have many microbes on them. There are some, but when we send it to Mars, for instance, we know that probably the conditions are so bad up there that anything that gets sent might die. If we bring back samples, are we bringing back potential life from another place? Where would you put it? What if it got out? That's the book Andromeda Strain. So all this stuff comes around to science fiction in a way. So when we do robotic missions, we're cleaning definitely, especially when we go to a place that's potentially habitable, has liquid water. The middle one, okay, if we want to bring samples back, where do we put them? This is the same kind of biocontainment that's being done with Ebola. You put them in biosafety labs. And then on top of that, you make sure they're super clean, because the last thing you want to do is have a dirty sample coming back from the moon or Mars or someplace else. You want it to be pristine. So you do that high level of Center for Disease Control type of biocontainment, and then you do additional pristine containment to make sure you don't mess up your samples. And we still have samples from the moon that are kept in pristine storage that came back in the 60s and 70s. And then we have questions about humans. You and I have lots of microbes in us. You might have heard about the microbiome. Okay, if I counted all the cells in your body, you have 10 times as many microbes in you. So 90% of you by number, not by size or mass, 90% of you is something else. 10% is my DNA. So you start thinking, oh, what's life? So when we talk about sending humans there, we're just now in the process of saying how many microorganisms can I send and still be okay? If I send me, is that okay? And how do I make sure I cleanly study what's up there? And if I want to come back, did you see the story today about the cruise ship and the woman that was the nurse down in Texas? And she was working with in the hospital where that patient died of Ebola. And then a couple of weeks later, she and her husband went on a cruise ship for vacation and then she found out the other nurse got sick. Guess what? She quarantined herself on the cruise ship, and the Mexican government would not let that cruise ship come into port. And that's where you start bumping into laws. So a lot of space law comes out of aeronautical law, which comes out of navigation law, comes out of maritime law. If you're on a plague ship, you're not allowed to come in. You go back to the port of port that you came out of. And so these things are very real. So how do you take laws that exist for reasons, for our health, for our safety, for regulations, for taxes, whatever, and translate them into places that are off our planet? And so that bottom picture there is actually when the astronauts came back from the Apollo missions. They were in a quarantine facility, and they stayed in it, and they moved that whole thing off the ship onto a cargo plane and then flew it to Houston and put it into, the astronauts were in quarantine for 30 days. And so, and we know a lot more about microbes and everything now. And when they did that for Apollo, EPA didn't exist. Center for Disease Control was a lot smaller than it is now. We didn't know about microbes. Our technology is way different. So all of the things we did during Apollo have to be redone. And so that's where we are. Then there's the question of, well, if we're going out there and you think about Drake equation, what if we discover what we're looking for? And plenty of science fiction authors have talked to us in books about what happens if we find something, and what are the implications of finding it. If you find intelligent life and you get a signal, you say, hooray, I got a signal. I can't tell you anything about the biology. All I know is they transmitted something. And as far as I'm concerned, I still go home and make myself a bowl of Cheerios and shop at the Safeway and all the same things. On the other hand, if I go to Mars and bring back a microbe, I could have a problem. So that depends on the kind of life that we're looking for. And since any one of those paths can be successful, we have to ask, what are the implications of it biologically, biosafety, outside in the environment as well. It isn't just humans that we worry about. It could be environmental change. Climate change is happening very gradually. What if the microbial changes happen very gradually, and then all of a sudden, oh my gosh, you've ruined the atmosphere or something? So you've got to think about those as well. And so when we're looking out there, we're looking not only when we're in our solar system looking for life, we're looking for microbial. When we're looking out further, we find a different kind of life that doesn't have the same biosafety considerations. Then we got the problem of asteroid defense. So it's not just the economics of asteroids. It's also what happens if an asteroid hits a planet and wipes out civilization. What happens when an asteroid is big enough to wipe out all the dinosaurs? It really happens. And so it turns out that there are people who are thinking about not only the economics of asteroid, who gets to use them and where do you mine, but also we start to observe the asteroids and talk about whether or not they're going to hit, then what's the technology you could use to push them out of the way, and how do you design and do the proof of concept for a mission that might push an asteroid away? And if it takes 10 years or 20 years, is that okay? But can you push them out of the way in 3 years or 1 year? But then you get the other issue, which is now you're talking the same thing like warnings. Think floods, hurricanes, earthquakes. You got warning systems. And if the astronomers are really good and can push it out of the way, it won't hit Earth. That's great. But if it's so big, or we didn't see it till later and it's still coming, now we know it's coming. What do we do to warn the people? And so I'm interested in all the decision making that gets made. Who makes the decisions about the risk? What size of an asteroid is worth pushing out of the way? What if it's on its way to China and the Chinese send up something to push it out of the way, and they get it out of the way so it doesn't hit Beijing, but now it's coming for LA. So you start to see there's an international dimension to it as well. And how do you communicate to the public? If I tell you that there's a 3.2 earthquake or a 6.2 earthquake, you know enough about Richter scale, or you know about flood warnings and wind speeds and things like that, or tornadoes. We've been educated about it. If the alarm goes off here and you hear a fire alarm, we know what to do. Duck and feel the door and all those things, look for the extinguishers. But what do people do when you tell them to evacuate because there's an asteroid coming? And by the way, it'll be here in 5 years. What do? Sell your house? Who's going to buy it? So how do you think about those things? So those are the kind of things that I think about. It's what's the story that makes a difference to us here on Earth, and how does finding things out there, whether it's signals from ETI or extrasolar planets or life on Mars, what do they do to here? And so I don't have any databases of things, but I have maybe the context that you can use. And I also have the need to think about how do you write the laws and the regulations when you're thinking about these issues. Pushing away asteroids, allowing life to come here or not, deciding who's going to settle on the moon or not when you can't have sovereignty. So there's a lot of legal and policy parts, and I'd be happy to talk to you about that. Thanks.
So I think we've got Jason and Doug, who are our last scientist speakers for tonight, and they get to talk about some really cool stuff too that happen to be exosolar planets and finding them and all of that fun stuff.
Thanks. Hi, I'm Doug.
Hi, I'm Jason.
So we're going to talk about Kepler and some of the different things it's doing. And I think, well, Jason doesn't know this yet, but I think I'll start with the first part of the data we collect with Kepler, and Jason will talk to you more about what it means and what we do with it. So Kepler, hopefully maybe you've heard of it, is a mission by NASA that was designed to find out whether planets, in some sense like the Earth, are common or rare. So planets that are about the size of the Earth and potentially habitable. So we're trying to answer the first two F terms in the Drake equation. What's the frequency of planets, and what's the frequency of, or maybe it's the N term, the number of planets in environments that potentially habitable. So I'm the Kepler instrument scientist, which means my day job is to sort of understand how Kepler's working and make sure it's still working. The data we're getting is good. And so Kepler is essentially a big digital camera in space. It's got 42 CCDs. This is an image of the full focal plane here. They're laid out in this nice pattern. And this is our first light image of the Kepler field of view. So this is an area of the sky. It's about 115 square degrees of silicon looking at the sky. And what Kepler does is extremely boring. During its main mission, it stared at this one spot in the sky, took a picture every 30 minutes for 4 years. And the more boring it was, the better it was for us, because we're looking for very stable images so we can look at the brightness of a set of stars in here and see if one of them dims a little bit as a planet passes in front of it. And then when that planet orbits its star and comes around again, it'll dim a little bit, a planet's year later, and then it'll happen again. And when we see these series of repeated dimmings, we can then look further at that signal and say, hey, really, there is a planet there. So what Kepler does is it takes, we don't have the data storage on board or the data downlink rates to transmit those full images down. It's about 95 megapixels, which when it was launched in 2009 was huge. It's not so huge now, but I think it's still the biggest that we know about CCD camera in space, so that's good. There are bigger ones coming, I think.
Key players know about.
Right, exactly, yes. There are other ones that are all looking down, so that doesn't matter. So Kepler has to define specific targets to look at. It doesn't look at all those stars. So what we do is we pick. I've zoomed in here on this big image. Is 1/4 of one of these modules is one CCD. Here's a blow up of that. You can see a whole bunch of stars there. This is a particularly interesting star. But in this little section here I've blown up, you can see the images when you look at Kepler aren't really all that great. Oops, I've gone backwards. It got out of control. They're not really all that great. The pixels are very large. The stars look like blocky squares. And when we actually want to get data for a star, what we're really looking at is this particular star, which is now called Kepler-62. We look at 6 pixels, and we measure the brightness of those 6 pixels once every 30 minutes for 4 years. And what we end up with is a series of these light curves or brightness measurements. This is just repeated. You can't really see very well the model. This is five copies of that same light curve, and on top of that 5 copies is the model of the 5 different planets we found orbiting this one star. These little drops in brightness. You can come up later and see it. A couple of them are more obvious. This is what Kepler's looking for, and this is the evidence of a planet. In fact, this planet F here, actually E and F here, are both sort of Earth-size habitable planets. So what we do with Kepler is we take these 6 pixels and we find this light curvy signal, and then we give it to the artists, and they draw a beautiful picture of what Kepler-62 might look like. And that's our goal. And this is a small, it's about 1.6 times the radius of the Earth planet orbiting in its habitable zone. It receives about the same flux from its star as Mars does. So it's cold, but if it has a nice thick atmosphere, which we have no idea, it could be, the surface temperature could be warm. And so this is what Kepler is trying to do. And I'll let Jason tell you more about what we found.
Okay, that's pretty cool. So we find Kepler finds lots and lots of planets. If you can walk away with one major lesson that Kepler taught us, that if you go outside tonight and there's a bit of a hole in the clouds and you see a star, there's probably planets around that star. That's the one major lesson you can walk away with Kepler. Of course, as the job of a scientist is finding all sorts of new discoveries, but you can almost think of it as taking lots and lots of numbers, say trillions and billions of numbers, and distilling it down into less and less and less. So for instance, Kepler has downloaded how many terabytes of data over 4 years, and we're distilling it down and telling you of those terabytes of information, there's thousands of planets in there, and we can tell you characteristics about each of those planets. So this is already out of date, but there's online data to tell you about it, and the axes here tell you something, the orbital period on the bottom, so how long does it take for a planet to go around its host star. So we take 365 days. So if you're around this particular planet, then you get a birthday every day. So I want to live there. And the other thing that you learn is that you can figure out the radius of the planet pretty easily as well. So that's the 2 main observables you get from Kepler. And of course, we also learn also things about it, like as you move further away from the host star, you can figure out how much light is hitting the surface, how much energy it's absorbing, which gives you an idea of its surface temperature, if it has a surface per se. And that can range anywhere from thousands of degrees Fahrenheit all the way down to minus whatever you want to think of. So there's a wide range of varieties. And of course, it all boils down to, again, taking billions of numbers and turning it down into a few essentially fundamental properties. This is sort of an artist's conception of the stars with these little black dots in front of it, is the planets that Kepler are finding. So we don't actually see pictures like this, so instead we use the Kepler data to envision what color is the star, because we know what kind of temperature it is, and we know how big the planet is relative to the star, so we can draw those little tiny black dots in front of it to give you an idea of the relative size to it. And if you come up and look close afterwards, you'll notice it's usually not just one black dot, but lots of black dots in front of it, because we're seeing lots of little mini solar systems, in fact, that are sort of reminiscent of our own solar system. That's sort of another of the key things that we're learning from Kepler. One of the main things we're missing is I can tell you how big it is, but I can't really tell you, at least with definitive accuracy, of what is the mass of these planets. So is it a gaseous ball? Is it a rocky surface? If it's something that's Earth-sized, I'll probably bet $10 that it's rocky, and if it's something the size of Jupiter, I might bet $50 that it's probably gaseous. But beyond that, it's hard to tell, because Kepler is an instrument that tells you the size, but not so much the mass. And that's sort of where the science comes into it from other aspects of ground-based observations, of trying to figure out that if you find an Earth-sized planet, is it rocky, or are we finding some weird ball of hydrogen that's floating around? And I think from all we're learning so far, using telescopes like the 10-meter Keck in Hawaii, is that if they're Earth-sized, they're probably rocky. But nonetheless, one of the links we gave you is towards what's known as the NextC Extrasolar Planet Database, which gives you every single number that we can think of for calculating about statistics of it, and we're more than happy to help distill that information for what you might want to learn about what these planets might be like. How big are they relative to the Earth? How hot are they? What sort of compositions might they be? And even some fundamentals like how far away is it? Is this something where you can just travel out to Saturn and you get there? No. Most of these are hundreds of light years away, but we can also get that information out as well. And I don't know, do you want to sum up with anything?
No, I guess we have available sort of this range of data from raw pixels to distilled tables of planet characteristics, and I'm not clear in my head on what exciting game you can get from raw blurry pixels, but maybe you guys can come up with something. The formats of that are more complicated, but we can try and help you with that. And any questions we're happy to answer. So. Thanks.
Happy we're done.
Thanks, guys. So I think now we get to move on to the really boring part, which is making games. Are you guys here to game jam a little bit? So now we get to really get into how do we take all this great data and work and knowledge that these SETI scientists have and see what we can do with it. How do we actually make something fun and exciting about it? How many of our scientists are staying around? Are you guys going to be around for a little while? So Jason, Margaret, Doug, and John, you're around. Frank. So we've got 6 or 7 of the scientists that are going to be able to hang around with us a little bit, and thanks, Pascal. So what we wanted to get into was to spend a little bit of time just answering any questions. So from all you guys that are able to start creating games, thinking of ideas, we want to see, well, what kind of ideas do you have? Do you want to sit down with some of the scientists and actually talk through some ideas? And I think Brandon's going to lead us through a little bit of a team formation exercise here before we even really get into that. Do you want to do that now? So I think with the rest of this, it's going to be a little boring for all the people online, but certainly stay on and hang out with us if you can or if you want to. But Brandon, do you want to come on up and lead us through some team formation for getting into the actual game jam inside of everything?
So is anybody here? Is there anybody here who needs people to work with before we even do this? Or did everybody come here with people that they are already to work with? All right. Looks like we've only got about 4 or 5 people who need a team, so maybe we just made a team. And my job got way easier. All right. All right. Raise your hands again if that was you. Celeste, Ryan. Yeah. Cool. Choose a table.
All right. So we've got a little bit of time before all the scientists have to kick it out of here. So I think what we should try to do is I wanted to see if we can do a little bit of a round robin with some of the scientists in each of the different teams, and then can just ask questions of them. Dive into any ideas that you guys have, and we've got about 40 minutes until I think the scientists have to take off. 40 minutes, 45 minutes. So how about we have all of our scientists jump in with one of the teams, and then in about 10 or 15 minutes we'll do a scientist rotation and get you guys to be able to talk with a few of them. Yeah, and everyone say bye to all of the people online for us. Thanks for hanging out with us, and hopefully we'll hear more from you guys over the weekend. And also, one last little local piece of knowledge for the people that are staying here. At night, these doors might lock. They probably will lock. So if you go out without letting anybody know and want to get back in, you might have to bang on a few windows. So please let one of us know. Brandon, myself, Karen's around, Ryan. Just if you do go out and the doors are locked, make sure that somebody knows that you need to get back in. All right. So yeah, hopefully just all the scientists can find teams, and then we'll do 15 minutes to catch up with the teams, and then switch around. All right.